Hey guys, this is just a little bit of guidance on the practice test 2 for the first business stat 2301 exam, just to help you cram before the test tomorrow. And without further ado, let's get into it. For question 1, whenever you have these problems, you're going to want to make a table automatically, starting with the numbered x values as a column, and then their corresponding values, which are 4, 3, 7, and 8. And when you have an operation like this, like you're gonna want to break it down and understand what it's asking you. So for this, you square each x, so you square an x value, then you subtract the mean, because that's what this is. Then you take the difference and square it, and you take that value, and then you repeat for all x values, so for 4, 3, 7, and 8, and then you take values and you sum them. That's what this is. So for the sake of time, I'll just do it for x1, maybe start with x2. Okay, so your total here is 22. You have 4 subjects, so over 4 is 5.5, which is the mean. So we'll make that a column. Mean 5.5, and it's the same all the way down, etc. Okay, and then xi squared. For x1, it's going to be 4 squared, which is 16, and then you have xi squared minus x bar, so 16 minus 5.5 is 10.5, and you have that squared, which looks like that, which is 110.25, and then you do the same for all these. You add down, your sum is your final answer. Easy peasy. Okay. Question 2. He takes 200 out of 2,000 homes. Because he's experimenting with the 200, that's a sample, and this is the population. Sorry, because this is the total number of number of homes in the area. So him inspecting 200 is the use of a sample, so that's option B. For 3, the statement that 40% of the 2,000 homes are in violation of city codes, that's a statistical inference, because he says 80 out of 200 violate codes, which is equal to a ratio of 0.4, and then he applies that to the total population of 2,000, which is 800, and he's saying, you don't even have to do this because it doesn't say in the problem, but he says 40% of the 2,000 homes are in violation of the code. He doesn't know that. He didn't do a census, which would be going to every home and seeing it. He inferred that with the sample, so that's a statistical inference. Easy peasy, right? For zip code is nominal because there is no hierarchy. Important part. For ordinal, there is a hierarchy. For nominal, there is not, because for nominal, let's say you have categorical data, which is hair color, eye color, anything like that. You can't have more hair color or more eye color than someone else, unless you're talking about saturation, but forget that. There's no hierarchy. You know, you can't have a higher zip, well, you can have a higher zip code, but that's not a scale or indicator of anything, really. So even though it's a number, there's no hierarchy among all the numbers. So another example would be phone number, because it's kind of the same thing with area code, whether it's like 202 or 782 or whatever. This one is not, it's not better. Not better than this one, even though it's higher. There's no hierarchy. Easy. For 5, it is ordinal because there is a hierarchy. A C plus is right in between a C and a B minus. All the time, always. It's always in between C and B minus, it fits there. But the distance between these is not 100% equal because it's a range, you know? Let's say this is like, these numbers are gonna be terrible, but let's say it's like 77 to 79, and this is 80 to 82, or something like that. I don't know. One person could have a 77, and one person could have an 82. The distance here is 5. Another person could have a 79, and one person could have an 80. Then the distance is only 1. So these are not the same, even though it would still be the difference between C plus and B minus. So because it's not equidistant, it is ordinal. Awesome. Okay, on to 6. When using Chebyshev's theorem to obtain the values within 75% of the values in a population with all, the interval generally will be wider than the interval for the empirical rule. So, empirical rule is 68% is plus or minus 1 standard deviation, 95% is plus or minus 2 standard deviations, and 99.7% plus or minus 3 standard deviations of the mean for normal data. And then Chebyshev's is a little different. It is whatever percent is 1 minus 1 over k squared, where k is greater than 1, because if you plug in 1 here, you just get 0%. It's not helpful. Anyways, it's wider because that's how it works. I'll do a little bit of explaining. Okay, let's move over here. So for 2 standard deviations, that's 95% of the data for the empirical rule. And then for 2 standard deviations, ignore that. Let's ignore the 75% because the question is just asking if you use the same percent of the total values, which interval will be wider. So let's use this because that's easier. And it's for the same set of data too. So here it says 95% is within 2 standard deviations of the mean, okay? And then you plug in 95% into Chebyshev's theorem, and it turns out k equals 4.472, which means 95% of data is, at least 95% of data is plus or minus 4.472 standard deviations of the mean. And it's for the same set of data, so the standard deviations will be equal. Obviously, 4.4 standard deviations is a lot higher than 2, so the interval's wider. And that's kind of it. I can't see there being too much more on that specific kind of thing. For Chebyshev's theorem in general, there will probably be more, but for that, not so much. Next page. My notebook, not on the test. So yeah, wider. 7. The variance can be higher or lower than the standard deviation. So keep in mind, variance is sigma squared, which is the standard deviation squared. Standard deviation is the root of the variance, which is just sigma, which is also this. This is variance, this is standard deviation. If variance is greater than 1, SD is less than variance. If variance is less than 1, standard deviation is greater than variance. You don't need to know the specific rule, but because of squaring, let's say you have variance equals 0.5, okay? Then your standard deviation will be 0.25. Your variance is 0.25, okay? Standard deviation will be square root of 0.25, which is 0.5, and 0.5 is greater than 0.25, so your standard deviation is greater than the variance. But if your variance is 4, then your standard deviation will be root 4, which is 2, and 4 is greater than 2, so your variance is greater than your standard deviation here. It can go either way. Okay, awesome. 8. The total number of data items, I don't know, honestly. I don't know. I looked in the slides. Just guess for that one. I can't help you, sorry. In observational studies, my handwriting's awful. Okay, observational means there is no direct manipulation. You are merely observing the elements in the study, and that's it. You're not changing anything yourself. You're just making inferences and observations on the present data, which means normally the independent variable would be manipulated, but because it's an observational study, nothing is manipulated. It's all just observed. Remember that bit of vocabulary. Okay, a sample is a subset of the population, and the sample mean can be larger, smaller, equal to, because it can, you know. If you have 100 people, average height is 5'9". You can get 10 people where they're out of the 100, and you can just randomly pick people that all happen to be really short, and their average height is 5'7". Or you can get 10 people that just happen to be on the taller side, and their average is 5'11". It just depends. But it should be somewhere close to after the actual thing. That's why we make statistical inferences from populations to, or from samples to populations. Okay, for 10A, descriptive is describing a group with data, and inference is inferring about a group, or it's usually a population, through a sample. Sorry, I can't make this. Yeah. I'll just use a little bit less paper. That's my border. Okay. Yeah. So for A, sample of 1K students, average is estimated to be 600. That is an inference because you're inferring from a sample to a population. And then B is 55th percentile. That's a descriptive statistic because she's using, or the pediatrician is using statistics to describe a subject somehow. There are a lot of different ways to use descriptive statistics. This is just one. Okay. Anyways, 11 is, okay, this one might throw you off. 11 is ratio. And you might be thinking, wait, why is it ratio? Wouldn't it be, I don't know. But with relative percents, there's a natural zero. Keep in mind, the difference between ratio and interval is they're both specific scales where each integer is equidistant. So like, you know, you have like each value is the same distance from each other, so it's a good measurement scale. But with ratio, there is a natural zero, which means zero is commonly occurring and represents nothing, I guess. So, or not nothing. Give me a second. It's a starting point, basically. Or not a starting point, but 0 means no statistic. So, I might have to cut this. Okay, Bill's running speed is 25% greater. It can also be 0% greater, which would mean it's just the same as Tom's. Yeah. That's it. Like, 0 is nothing, basically. So it's ratio. You might be confused because like he still has a running speed, obviously, which is that of Tom if it's 0. But what it's asking is the percent greater than Tom, which can be 0. And that would mean he's not greater than Tom at all, speed-wise. So yeah. You have to keep in mind the statistic it's asking you about, and be careful not to confuse that with anything else. Okay, for 12, that is ordinal because there is a hierarchy, but no good scale. So you don't know if everyone below her had scores that were all the same distance from each other. For 13, it's nominal, obviously, because it's categorical data. For 14, it's also nominal, because it's a number, but you can't have more of a social security number than someone else. Everyone has a somewhat random, how many digits is that? 9? Yeah, random 9-digit social security number. And it's not hierarchical. There's no hierarchy. Okay. 15, the mean post-test score for the weight of the experimental group exceeded that of the control group by 50 points. This is also ratio because there's a natural 0, which would be no excess of the score, and there's a proper scale. For 16, these are ordinal because it's ranking. For anything that's ranking, it's not guaranteed that each place is the same distance from each other. It's very unlikely that's the case. Awesome. Okay. Let's move on to Exhibit 2. Blah, 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 blah. A researcher hypothesized that athletes who use PEDs have higher aggression levels than athletes who do not use PEDs. On January 7th, using a 7-point Likert scale, he measured the aggression levels of a randomly selected sample of 32 football players who had used PEDs and a randomly selected sample of 34 who had not. He concluded the population of athletes who have higher aggression levels than athletes who had not. Okay. This is an example of inferential analysis, because it's an observational study. He didn't do a test. He just surveyed, or he didn't control the variables. He didn't manipulate the variables himself. He just measured the stuff, surveyed, asked questions, and got answers. And it said that, people using PEDs are more aggressive. Okay. Inferential analysis. Awesome. 18. Refer to Exhibit 2, the student example of cross-sectional, because it says on January 12th. Cross-sectional is like a snapshot, is what some people call it. It is just something at one time, compared to a time series analysis, or longitudinal study, which I think are synonyms, and those are continuously checking on test subjects over time. 19, it is observational because, again, he's just observing. He's not giving the athletes PEDs or not and having a control and test group. He is just splitting the ones who already had and already had not, and then observing and stuff and making conclusions based on that. Okay, 20. I'll just go along with the definitions here. An element is a subject. So it would be a football player in one of the sample groups. Okay, parameter is just the guidelines for the study. Statistics is that's a statistic, and a confounding variable is something that might influence your conclusion. So an example is like, if you have height among just total population, you're gonna have it really high around 5.4, and then, or you're gonna have a lot of data at 5.4 and centered around there, and then a lot of data centered around 5.9, because those are average male and female height. So gender there, or sex there, would be a confounding variable. That's what that is. And so it is a statistic. I think we all know what a statistic is, and it's not the other ones. Okay, 21. Aggression levels are remember, he used a Likert scale, which is ordinal, which means it can't be quantitative, because remember this, only interval or ratio can be quantitative. That's an important distinction. And discrete or continuous are also only for quantitative. So it is E, none of the above. Okay, and then 22. Independent variable is, that is what you separate by to get the dependent variable. So he separates the athletes by use of PEDs and not use of PEDs, because he wants to find whether that has an effect on aggression levels, which is a dependent variable. So this would be use of PEDs. And then the dependent variable is aggression levels. Okay, 23. I said that. Dependent variable is aggression. Likert scale is ordinal, so for 24, it would be ordinal, because there's not an equal distance between, like, okay, great, fine, bad, and very bad, whatever that is for the Likert scale. Okay. We have a kurtosis problem for 26. Remember, for skewness and kurtosis, the normal range, this is on your formula sheet, is plus or minus 2 times standard error. And if your value is within that range, then you're good. It's roughly normal. You can proceed with the empirical rule and such. And if it's outside of your range, then it is not normal. You have to use Chebyshev theorem and stuff like that. So here you go. Let's start with skewness, just because standard error of skewness is 0.32. Multiply that by 2 is 0.64. So we have negative 0.64 to positive 0.64. Sorry, that looks like something like that, okay? This is your range. 0.85 is right here. So it is, since it's higher, it is positively skewed. And then standard error of kurtosis is 0.27 times 2 equals 0.54. It's negative 0.54 to positive 0.54 is your range. And then the kurtosis is negative 0.85. Sorry. Negative 0.85 is outside of the range. So it is platykurtic, like a platypus. It's very flat. So the data would look something like this. I'm gonna write it here. It's very flat. Okay, I don't know about that flat, but, and then it's skewed to the right, which means it's gonna have a long tail to the right. So it would look something like that. So it is positively skewed and platykurtic, which is C. 27. It's a percentile question. This tripped me up. Percentile rank of a score of 57% on a quiz is 74. That means the score on the quiz is 57%. Percentile rank is 74%. And we know what percentile rank means. That means that 74% of people scored at or below this score, which is 57%. This is the actual score. This is how many people got at or below the score. Read closely, guys. So it is D. Okay. Let's go to 28. Blah, blah, blah. Important stuff is mean is 21, standard deviation is 3, skewness is 0.78, and standard error is 0.24. So what we want to do first is see if it's inside or outside the standard error, or inside or outside the range of normality. So we do 0.24 times 2, which is 0.48, and then plus or minus that, so our range is negative 0.48, positive 0.48. 0.78 is outside of that. It would be here. So it is not normal, which means we have to use Chebyshev's theorem, which is whatever percent is 1 minus 1 over k squared, blah, blah, blah. Whatever percent, all right, so you plug in the number of standard deviations from the mean, you get the percent of the data that fall within that range. So, just looking at the answers, you kind of just mess around and tinker with it until you get it. Standard deviation is 3, and your mean is 21. So, one standard deviation is between 18 and 24. 2 standard deviations is between 15 and 27. So this is 1 standard deviation and 2 standard deviations. And for this, 75% is for 1 minus 2 squared. So like you solve this, you get 75%. So let's use 2 standard deviations because 1 does not work for Chebyshev's. If you plug in 1, you get 1 minus 1 over 1, which is 0, does not work. K has to be greater than 1. So let's use 2. Okay. You get 75%, and then would you look at that? The answer's right there. Approximately 75% of middle-aged men walk a mile in 15 to 27 minutes. I'll do the problem again. You can't use 1 standard deviation because it doesn't work for Chebyshev's. You know it's not normal, so you have to use Chebyshev's. So you use 2 instead. Let's do that right here. 1 minus 1 over 2 squared is 1 minus 1 over 4, which is 0.75. So 0.75% is within 2 standard deviations because that's the K value we used. 2 standard deviations is 15 to 27 because you go 21 plus 3 plus 3, and then 21 minus 3 minus 3. So it is E. Okay, 29, 99-point scale. You should automatically know that's ratio because it's a scale. All the values are equidistant from each other. There's a natural 0, which is getting a 0 on the thing, or having no stress. Sorry. Blah blah blah. The box is just the mean symbol. So mean for afternoon is 75, and mean for morning is 57. And then the weighted mean is 63. And so let's just find the intermediary value between these 2 scores, which would be just the mean between them, to see if they were the exact same size. This mean would be the weighted mean, and then we'll go from there. We'll compare the 2 values. So 75 minus 57 is, I don't even know, what is that, 18? Give me a second. 18 over 2 is 9. So we'll do 75 minus 9, or 57 plus 9. Plus 9 is 66, which is the unweighted mean, or unweighted mean. And since the weighted mean is closer to the morning class because that's lower. I'll write it down like this. You have 57, then you have 66, then you have 75. This is the morning, this is the afternoon. This is the unweighted. This is pulling the mean more than this is, which is why the mean is closer to that at 63. So we know that this class is bigger because samples with higher populations, or samples with larger numbers, or sorry, groups with larger sample sizes, however you want to put it, that draws the mean more towards it. So you know the morning class is bigger. So sorry, blah blah blah. Okay. For 30, I hope you know it's categorical data at this point, which means you either use a bar chart or a histogram. Bar chart looks like this, where the values are not touching, and a histogram looks like this, where the values are touching. You want to use a bar chart because it's categorical and it's not touching. That's kind of it. Awesome. Okay. 31. For ease of data entry, 1 denotes that the student originally enrolled, and 2 is a transfer. These data are categorical because they just represent some categorical characteristic, whether the student is originally enrolled or a transfer. This is what it represents. Don't pay attention to the fact that they're numbers. They represent this, and this is categorical. Awesome. Okay, 32. Reported most profitable corporations of 2013. That is somewhat of a snapshot, so that's cross-sectional data. 33. Blah, 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 blah. Relative to the mean, so you want the deviation score, which is standard deviation over the mean. Sorry, I should be using the S, but I like this better because I don't want it to look like an S or a 5, even though you should be using the S with the mu symbol, whatever. 180 is the standard deviation over 900, which gives a deviation score of 0.2. And then the other one is 240 over 1600, which is DS of 0.15. So this deviation score is higher than this one, so that means overall the data is going to be more deviated from the mean, which means further from the mean, more separated from the mean, however you want to call it. It's going to be more dispersed relative to the mean compared to this, because the deviation score is higher. Okay. Okay, this is fun. This is something like a frequency table problem. All right. You have, I'm not going to put the supply because that's just letters, that's irrelevant. You have the price per gallon, 23, 25, 29, 27, then you have the number of gallons, which is 700, 200, 100, and 200. Determine the average price per gallon that it paid. So, the easy way to do this is just a weighted mean if you want the average price per gallon here, and they're not giving you like frequencies and relative frequencies, probabilities, blah blah blah, stuff like that. So you just multiply these. So 23 times 700 is 16,100. And you get all this and you divide by the number of gallons, the total number of gallons, which is 700 plus 200 plus 100 plus 200, 1,200. Sorry. 1,200. There you go. This is the total number of gallons. You get all these, you sum them, and then you divide by 1,200 gallons to get the average price per gallon. That's it. Okay. We have a frequency table problem next. This is very important. You must know how to do this for the test, okay? You have country, and then minutes with dad, which is just, that's the frequency. Okay, I'm gonna abbreviate these. US, Canada, Sweden, Finland, China, and then 30, 36, 42, 42, 44, 46, 50, and 54. And then you're obviously going to want the relative frequency. Whenever you have a frequency like this, sorry. Hello. Please focus. Crap, dude. Okay. Whenever you have these, you always want the relative frequency, or almost always. Rule of thumb, you always want it. So we add these up. That's 36. To get 346. Let me double check that. It's 344, I think. Yeah, 344. This is the total. And you divide all by 344 to get the P of x and f of x are the same thing. This is the relative frequency, so how much this shows up in total. So if you think of it as a pie chart, it would be like what percent of the pie chart it takes up. Because it's a proportion, so. And use a lot of rule of thumb, round to 3 decimal places. It's different stuff is gonna say different stuff. This says final answer round to 2 decimal places, but all the numbers are relatively small, so you want 3 decimal places for all the working numbers. And then you just do each number over 344. So 5. That's the same. 0.128, because I'm rounding, 46 over 344, 0.138, because I'm rounding, or 134, sorry, because I'm rounding, 50 over 344, 0.145, 54 over 344 is 0.157. Okay, and then you have these, you have the relative probabilities. These should all add up to 1, which they do about. And then, what's it actually asking for? The mean is just, obviously, add all these up, which is 344, divide by the number of subjects. There are 1, 2, 3, 4, 5, 6, 7, 8. 8 subjects, so 344 over 8 is 43. The mean is 43. It's kind of nasty looking. Okay, Q2 is the median. For all the quartiles, you use the whatever it's called, interval formula thing, which is I of whatever thing is the percent you want of your percentile. So whether it's 50th, 75th, 25th, or something else maybe, over 100 times the number of subjects plus 1. So for this we want the 50th percentile, which would be 50 over 100 times 8 plus 1, which gives us, this is 1/2 times 8 plus 1, which is 9. 4.5 is the median. Q3 is the same thing. I-75 equals 75 over 100 times 8 plus 1 is, so 9 times 0.75 I think is 6.25. 6.75. That is Q3. And then I-25 is 25 over 100 times 8 plus 1. And this is 2.25. Which is Q1. And then IQR is Q3 minus 2 Q1, so 6.75 minus 2.25 is 4.5. That's your IQR. Which is the same as the median, but whatever. Okay, and then the mode is where the most data points lie. That's 42, because there's only one data point for every other value. Standard deviation. This is a bit tricky. On your formula sheets, the standard deviation formula is the sum of the x values minus the mean squared times f of x. So we're gonna have to do that. I'm pretty sure. Or you can use computational formula. But for the sake of learning, we're gonna use this because a lot of times you're gonna need to have this and have the whole frequency table set up. So let's just do that. You have the frequencies, or the x values, or no, these are the frequencies.